Good morning, everyone. Today is June 12th, Monday. We're going to record our next session. And before we record and tell you what we are trying to do, let me go to Blaze View and show you where things are for a second time, let's say. And that's okay. I'm not complaining. Um, Here's our Blaze View page. And again, what you see will look a little different from what I see, but I think most people are doing fine. I still get a few questions, so I'm going to clarify a few things. So, class video links. This is where I am going to record all the I'm going to record all the videos and upload the links. Okay. Office hours are here. You can come and meet me anytime between 8:30 and 9:30 on Mondays and Wednesdays. If these time slots don't work for you, you can schedule an appointment. We can talk one-on-one. Okay. I'll be happy to show you my face. Okay. Go to day one, watch the couple of videos. That'll only help. All right. Now, these links, uh, these announcements will kind of move a little bit, but I won't change the office hour link. It will always be here. And the video links can go up, can go down, but gradually more classes will be added. Again, how do you access your book? You go to the student links and you go to this link, My Lab, Statistics, Pearson, eText, and you'll get it. Okay, I'm not going to go. It takes a couple of minutes. You have the whole book. By the way, today we'll work on 5.2. By the end of the day, after you watch the video, you should be able to do most of the problems from 5.2. If you cannot do a couple of problems, you can ask me, clearly give me the screenshot. Okay, give me a clear screenshot as large as possible. You don't have to get carried away. I will be happy to do it. My lab, statistics, all assignments, homework. Let's look at homework. Okay, right now, two of the sections have been uploaded. I'm assuming you won't be able to do 5.2 today, but you should be able to do 5.2 after listening to the whole class. Okay? I hope that helps. Now, what are we doing today? What we're doing today is a problem from 5.1. A student from our class asked me to do it. I will do it right here. Interestingly enough, the answer is here. That's okay. So let's read the question. I don't know how well you can see. I can make it a little bigger. Okay. So remember, guys, let me grab a slide, okay? I do need a slide. So let's read the question. Bob is asked to construct a probability model for rolling a pair of fair dice. We're going to assume it's a six-sided dice. If nothing is mentioned, it's a six-sided die. He lists the outcomes as 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Because there are 11 outcomes, he reasoned the probability of rolling an 11 must be 1 over 11. What's wrong with Bob's argument? Clearly, the implication is it's wrong, and it is. And I will explain it to you why it is wrong. All right, guys? So let me go back. And okay, the outcomes are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why? Because when you're rolling two dice, you could get 1, 1 and 1 or 2, that'll give you 3. You could get your sum, and you're looking at the sum of the two outcomes. Well, the minimum sum is 2, and the maximum sum you can get is 12. You could get 6 and 6, that'll be 12, and you could get 1 and 1, that'll be 2. You'll never get a 0 or 1. On top of that, you will get everything in between 2 and 12. Okay? How do you get 3, right? Maybe 2 on one, 1 on the other. How do you get 4? Maybe 2 on one, 2 on the other. How do you get 5? Maybe 2 on one, 3 on the other, so on and so forth. I hope you understand it. Let's look at the sample space from our last class, okay? You've seen this slide before, okay? Don't worry about that. That's not important whether you've seen it or not. Right here. So you want to keep this handy, all right? When you take the exam, you'll see questions about this. So you want to keep it handy. Now, I'm not going to worry too much about the question. I hope we understand the question. I need the room on my computer screen. So here, take a look, guys. Your sample space should be described as follows, what you're seeing here. Um, Look, there are really 36 outcomes. There are really 36 outcomes, and you can get two only one way. You can get 12 only one way, one out of 36. Probability that you'll get a 12 is one out of 36. One out of 12. The probability that you'll get a 2, sum of 2, is also 1 out of 36. All right. Now, you can get a 7. Look at this. This is the most likely number you will get. You can get a 7 in so many different ways out of 36. You can get a 7 if you roll a 6 and a 1, 5 or 5 and a 2, 4 a 4 and a 3, 3 and a 4, 5 and a 4, 5 and a 2, sorry, 6 and 1. So the probability that you'll get a 7 is 7 over 30, sorry, 6 over 36. Let me erase that. Sorry about that. Let me write it down nicely, okay? So that you can review when you review it, it looks a little nicer. The probability that you'll get a 2, I'm going to write it like this, as follows. The probability that you will get a 2, of getting a 2, is not 1 out of 11, it's 1 out of 36. What's the probability that you will get a What's the probability that you will get a 12? Well, also, for the reason that was explained a minute ago, is also 1 out of 36. But what's the probability of getting a 7? Well, you can get a 7 in 6 different ways out of still 36. You can write it as 1 over 6, 1/6. Okay, so I'm going to go back to the question and kind of use the language the book expects you to use. So be a little patient. So this is the explanation. Clearly, it's not 1/11th. It depends on the number, and the outcomes have different probabilities. When you have a sample space where the outcomes have different probabilities, we call it a non-uniform sample space. It's a fancy word. I don't know if your book describes it, but here it is. So what are they saying? The experiment does not have equally likely outcomes. Sure, you can say that. That's a good way of saying it. The outcomes have different probabilities. That's another way of saying it. You could also say the sample space is non-uniform. I don't think your book uses it. Otherwise, they would have used that term here. So again, this is not correct because the outcomes have different probabilities or the outcomes are not equally likely. I hope that helps. Once again, if you can't answer a couple of questions, always feel free to ask me, come to the office hour, or it's only 2 days a week, but most people don't have time exactly when I assign my office hours. So you can always make an appointment and we can have a conversation one-on-one. All right. I can't reteach you the whole content that way, but I can certainly help you with your little issues. All right, guys. Now we're going to start section 2, chapter 5. All right, guys. Now you're going to see that some of the things will seem a little challenging, okay, today for the first time. So be a little alert. That's all. Nothing too serious. All right. So, well, first things first. let's define a couple of terms. Okay. Disjoint events. All right. Disjoint. The good news is it is what you think it is. All right, guys. That's the good news. So be a little patient. I would like to believe by the end of today, you should be able to do all the problems from our 5.2 sections. Okay, if not, that's okay. We'll pick it up tomorrow. No big deal. At the end of the world. So, what do we mean by disjoint events? Okay, you can look at the definition given in your book. I'll say it in my own words. Okay. All right. So, guys, I'm rolling a six-sided die. My sample space is, as we know, I'm rolling only one die. My sample space, by the way, we use curly braces like this. One, two, three, four, five, six. Okay. Two events. What's an event? A little bit of review. An event is a collection of outcomes, right? So let's say I am interested in this event of getting an even number. I'm going to write it even. Event of getting an even number is 2, 4, and 6. Okay. I'm also interested in another event, an event that involves getting an odd number. I'm going to write O. I'm going to actually write odd because O looks like 0. And just to let you know, you really want to understand these terms. I'm not going to ask you to define them, but I will use them on the exams and the homework problems. Once again, the exams I will make will be available on BlazeView, and they will be very similar to MATLAB homework problems that you guys are solving. All right, guys, let me fix that. I made a mistake, 3 and 5. Okay, these two events have nothing in common. They are disjoint events. All right. So the events of getting an even number is 246, and the event involving getting an odd number is 135. They have nothing in common. There is no excuse me, there is no overlap. So if two events have no overlaps, no outcomes, no outcome belongs to both events or more events. We'll generally talk about two, maybe three a little later. We will say they are disjoint. They are not connected. So let me give you an example of another example of a disjoint event. Okay. This time I'm going to say numbers less than 3. Less than 3. All right. And I can only come up with one. Of course, I'm rolling a single six-sided die and numbers greater than 3. All right. Got numbers greater than 3. I didn't say greater than or equal to. You have to be careful. You probably know that by now. These are the numbers that are greater than 3. Is there anything that's common to both events? The answer is clearly no. Okay. So, sorry, 4, 5, 6. The statement is still true. These two events, greater than 3, will have 4, 5, and 6. Less than 3, will have 1 and 2. They have nothing in common. They're also disjoint. Okay. Now, I'm not going to write it. An example of not disjoint event or we don't use the word joint event. I don't know why. We just don't. So let's have an event that involves 1, 2, and 3. I have another event that involves 3, 4, 5, and 6. These two events are clearly not disjoint because 3 belongs to both. I hope you understand the meaning of the word disjoint. Moving on, a few more terms to sort through. Okay, all right, another fancy word, and you're going to hear it a lot. Well, they're related, okay? Mutually exclusive events. Let's move things around a little bit. Okay, two events are mutually exclusive if when one happens, you know the other is not going to happen. Okay? So they have to be mutually exclusive events, have to be disjoint. All right? When this happens, you know the other one didn't happen. If I say I roll a die and I got number less than three, you know I did not get a number greater than three. So two events are mutually exclusive if when one happens, the other one doesn't happen. Let me go back to your text, okay? Give me 1 second. Let me see how your text defines it. It'll be a nice connection we can make. Give me 1 second, okay? Because there is a little, it's not a glitch. Sometimes people add another term to the definition. So let me find out how your book does it. It's my way of showing you how to use the book. Go to the contents. You're looking for chapter 5, section 2. So they talk about disjoint event. They show you a nice picture. You use the book, okay? So talking about disjoint events. We're going to come to addition rule. Don't worry. Well, anyway, we're going to stick to our definition, okay? Mutually exclusive means when one happens, the other one doesn't happen. All right. That's good enough. I couldn't find it. I'm not going to waste your time right now. All right, guys, one more term. Complementary events. Okay. All right. So I'm going to first, they're connected. Okay. Now, once again, let me give you a little summary. Mutually exclusive events and disjoint events are really synonymous. They're really the same thing. You're going to hear both terms. All right. And we use them interchangeably. Let's talk about complementary events. Another fancy word, complementary. Okay. This is not a typo. This E is E, not I. All right. Complementary events. Okay. Okay, complementary events will always be mutually exclusive. Okay, on top of that, complementary events, generally we use two events here, not more than two. Complementary events will form the sample space. So when two events, let's define it. When two events are mutually exclusive, and when you put them together, you get your sample space. You call it, you call the events complementary events. For instance, I'm going to say event A involves this, and event B involves this. Now, they are not complementary here because three is missing. Yes, A and B are mutually exclusive, A and B are disjoint, but they are not complementary because they don't form the sample space. So if you put three here, or anywhere really, if you now say A is 1 and 2, B is 3, 4, 5, and 6, they together, they together form the sample space. So now these two events are complementary. All right, the good news about complementary event is this. is this, and something you want to remember. Probability of A is going to be, in this context, 2 over 6, which turns out to be 1/3. We're not going to worry about it. And the probability of B, event B, what's the probability that you'll get a 3 or a 4 or 5 or 6? Is 4 over 6. Guess what? Guess what? When you add the two probabilities, you get 1. Okay? You get 1. 2, 6 plus 4, 6 is 1. And that's good news. If I say two events are complementary, all right, and you know the probability of one event, you can find the probability of the next one just by subtracting that probability from one. Let me give you an example on a different slide. Okay, suppose, okay, I'm not even concerned about using a die or anything. It's true for any two complementary events. And the probability of A is 1/3. Okay, find the probability of B. Right, let me go to the next line. Find the probability of B. Find here B. All right. So now, if A and B are complementary, another fancy symbolism you kind of have to remember. The complement of A is labeled this way. Com A. You can write it like that. I've seen it. A to the power C. Okay. That's how we label complement of A. Okay, this is red. There's a little C on top. You call it complement of A. That's how you read it. You can write it compare. Some people actually write it like this. It doesn't matter. You should be familiar with both. I'll probably use this notation. Okay, some people will put a bar. But probability, if A and B are complementary events, B is this. B is this. So what's the complement of A? Well, what's the probability of A complement? It's 1 minus 1/3. What's 1 minus 1/3, guys? 1 minus 1/3, if you remember your fractions, is going to be 2/3. So the probability of B, sorry. So the probability of B is 2/3. I hope that helps. We're going to use this a lot, okay? If you know the probability of an event, you can easily find its complement by doing what we just did. Okay, guys? Moving on, moving on. See what else is coming up. So we defined a bunch of terms, okay? Disjoint, mutually exclusive, complementary. Another thing is we're going to talk about this. All right, let's take this slide and bring it here. What is it saying? Addition rule for disjoint events. So if you're dealing with probabilities and you know they're disjoint, so you know they have nothing in common. For instance, you're talking about people who were born in Georgia and you're comparing that set to the people who were born in Florida. Of course, there won't be anything in common. Okay. So in that case, if I want you to find the probability of E or F, you can simply find the probability of E and probability of F and add it. Okay, intuitively, that's what you would think, and that's exactly how it works. Now, I want to emphasize something here in English, in math actually, and even in English. You really have to be careful about the words and and or. All right. Or means either this or that or both. Actually, that's what it means. Okay. Once again, I'm going to draw a circle and explain it to you. So these are the people who like, what should I say, bananas. These are the people who like apples. Let's write it down. Okay. So I'm explaining a difficult concept. It's something we think students should know, but deep down inside, sometimes students don't know. I'm kind of going over it. So I'm talking about the difference between and or. We will stick to this definition that I'm giving you. Apples. I'm just going to write A if you don't mind, and I'm going to write bananas. Okay. All right. So this rectangle represents everybody. Okay, people who don't like apples, who don't like bananas. I'm not going to go over sets. It's necessary. That's all you need to know. So guys, again, if I say I am going to invite my friends who like either apple or bananas. Okay. If you dislike both, we're not going to invite you. I know it sounds a little silly, but you get the point. So that means what, guys? This overlap, who are these people? These are my friends who like both apples and bananas. There is no way I can say, oh, you like both. I'm not going to invite you. You will always invite them. Again, A or B means either A or B or both. When I say and, when I use the word and, I am referring to just this overlap. If I say, I will invite my friends tomorrow evening who like apples and bananas. They have to like both. These guys will not be invited because they don't like bananas. And these people will not be invited because they don't. I'm sorry, guys. The first one, let me go back. I know I misspoke, but I know most of you would have caught it. So I can't, if I say I will invite both people who like both apples and bananas. I cannot invite them because these people only like apples, but they don't like bananas. I am not inviting them because these guys like bananas, but they don't like apples. I'm only inviting this overlap. Okay. Overlap represents and everything inside the two circles represent or. All right. And you really want to keep it straight. And if you have to watch this little clip twice, by going back, please be my guest. Once again, or means either A, or all of B, or who belong to both. Now, when we talk about disjoint sets, there won't be any overlap. There won't be because that's how disjoint sets are defined. So if I say in my class, in my friends, I don't have anybody who likes both apples and bananas. Either they like bananas or apples, and some of them don't like either one. So the picture will look like this. Okay. These are the friends that like bananas. These are the friends that like apples. And so, so I hope you understand the connection between and or and the word disjoint. And the word disjoint and mutually exclusive kind of mean the same thing. All right, guys. Now, what they're saying is that if E and F are two disjoint or mutually exclusive events, then probability of E or F, again, or would be if you know the probability of E and if you know the probability of F, you can always add them and you'll be good to go. Now, this sounds good so far. I'm sure it does. I hope it does. But there is a little problem when you have an overlap. Let's see. All right. Let's see. Now that's what makes it a little hard. What happens if the two sets are not disjoint? They overlap, all right? So guys, I am going to use my apples and bananas. That story was okay. That's fine. Now I'm going to use E and F, okay? Now, look what they're doing here. You really want to understand it. If two events, general addition rule, when they say general, that means they're not disjoint. They don't have to be. Okay? So for any two events ENF, that means you cannot assume they're disjoint. That means there is an overlap. There is an overlap. E and F quite likely overlaps. If they don't overlap, the overlap is zero. Don't worry. E and F overlap like so. And clearly this football, where the two circles overlap, is the part, as we have discussed, is this. Okay? So they are saying if two circles are not necessarily mutually exclusive, the probability of E or F will be probability of E plus probability of F minus probability of E and F. They have to subtract this. Now, it's actually not that difficult to see, guys. The reason we subtract it, when you find the probability of E, you're including the football. When you're finding the probability of F, you're including the football, and the football shouldn't be counted twice. Okay, that's why you subtract it once. So you have to remember those two formulas. And when you sit to take your exam, make sure your formulas are handy. Write them down on a piece of paper, keep them handy, label them as 5.1, 5.2, so that you don't have to go back to the book and all that. So I hope that helps. It's a little difficult concept, okay? Hopefully it'll make a little more sense when I will do a couple of problems. I'll do a couple of problems today, okay? Another thing I wanted to mention, guys, is this, okay? Hopefully you can, now let me bring it here. All right, hopefully you can see, okay. I, I'm not promoting card playing. If you play, fine. If you don't play, that's your problem, not a problem. But if if you have to know the deck for this class, you have to be familiar with the standard deck of playing cards. There are tons of problems that will involve this idea. And I'm going to go over it briefly. All right, most of you know, I know that, what a deck looks like. Half of the these, I don't know how well you can see. I can make it a little bigger. I can make it much bigger, really. So this is A, it's ace. This is a suit. Okay, S-U-I-T. These are called spades. It's black. The second suit here is hearts, red. They are red. The third one is clubs, and they're black. And the fourth one in my picture are diamonds. Each suit has 13 cards. Okay, and there are 52 cards in a deck. One more thing. These are called face cards. For obvious reason, there is a face. Jack, Queen, King. These are called face cards. So what I would recommend is that either you take a picture, keep a standard deck handy when you take the exam. If I give you a problem from this area, you'll be able to handle it. All right. So you want to be familiar with standard deck of cards, and you want to know how many cards are there. You want to know what colors they are. There are only two colors. You want to know what the suits are called. You want to know what the face cards are. Right, guys? It's going to help you. I'm not going to go over it every day, but I did today. It's kind of our, the first part of the semester. So no problem. We did this. We're kind of wrapping up. Let's try this problem. Let me see. According to National Government Study, 52% of Americans have played state lotteries. What's the probability that a random select person? Okay. All right. Good. Let's try it. So this one is a problem from your book. Um, I know you can see let me see if I can. I'll hide the solution. You can just read the question. This is an example from your book. According to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. Okay. What's the probability that a randomly selected American has not played a state lottery? So to me, these are complementary events. You either play or you don't play. All right. There's nothing in between. And one more thing, they are disjoint. They're complementary events, and when you put them all together, they form the whole sample space, which is all Americans, and they are clearly disjoint. So that's easy. By the way, 52 is 52 over 100. Now you can write it that way. It really doesn't matter, but I'm going to do it today. You don't have to. 52%. Let me find out. If we had a percent, yeah, right here. 52% is 52 over 100. That turns out to be, if you don't mind, I'm just going to write 0.52, and you can always do that. Okay. This is the probability that if you draw a name out of a hat, if you can theoretically put all the names of all the Americans in a hat and you draw it, 52% of the time you're going to get somebody who has gambled or whatever term they're using, who played state lotteries. Okay. So what's the probability that they have not? Okay. So I'm going to write it like this. So probability that they played state lotteries is 0.52. Okay. The probability that they didn't play state lotteries, since they're complementary events, not played state lotteries, is going to be simply 1 minus that number. And that turns out to be something like, if I'm not mistaken, 0.48. Let me double check. 910, that sounds about right. So this is how you use the idea of complementary events. And we talked about it. We did one example. When you do more problems from your book, things should gel a bit more. All right, now we have one more problem. This is 26 from 5.2 from your text. Okay, there are problems like this in your MATLAB packet. Of course, you can do some of the problems from your book if you want to, but here is a problem from 5.2. So if you scroll down your text in chapter 5.2, when you're done with chapter 5.2 or chapter 5, section 2, you're going to see a set of problems. This is number 26. Let me see if I can do it carefully without making too many mistakes. All right, I don't know how well you can see, but you have your book. I'm going to make it a little bigger. So let's read it carefully, okay? The following probability model shows the distribution of family structure among families with at least one child under the age of 18 years of age, under child younger than 18 years of age. What they're saying is they're looking at all the American families that that have at least one child younger than 18. Okay. Now, there are different types of families. Two married parents, first marriage, two married parents, one or both are remarried, single parent, cohabiting parents, that means parents who are living together, and no parent at home. All right. Now, verify the probability model. Okay, let's go over it carefully, guys. When you verify the probability model, when I read these, I know they're disjoint. Okay, they're disjoint, but they should all add up to one. Okay, all these probabilities should add up to one. Let's use a calculator to check it. All right, where am I? Sorry, let me find it, okay? I need a calculator. Now, I did check it. It is a probability model. All right, let's see what we can do. Very carefully. I don't know how well you can read it, okay? I hope you can. All right, 0.46 plus 0.15 plus 0.26 plus 0.08 plus 0.05. Good, I get one. So all the probabilities add up to one. I don't have any negative numbers. Things make sense. All right, you always want to check it. I'm not going to give you a problem where the probabilities don't add up to one. I won't. But when they say verify the probability model, that's really what you want to do first. And of course, the probabilities cannot be negative. Of course, they are not. Probabilities cannot be like more than one. Of course, they are not. We can see it. All right, so verify the probability model. We did. What is the probability that a randomly selected family with at least one child younger than 18 of age has two married parents in their first marriage? Well, that's easy. If you read it carefully, they want you to look at the first group, and I'm getting 0.46. Nothing too fancy. Okay. Well, let's do it here. If you don't mind, I'm going to call it B. The answer to B is, again, you have to read it carefully. If you can read it, go to your book. Okay. Take a nice picture, make a big slide. Uh, Interpret this probability. That means, how do you interpret the probability? Not a big deal. About 46% of the parents with one child younger than 18 are in the US. That's what they're saying. It's 46% of the parents are in their first marriage with a child younger than 18, however you want to say it. What is the probability that a randomly, I'm moving to part C. What is the probability that a randomly selected family with at least one child younger than 18 of age, 18 years of age, has two married parents? Now, two married parents. Okay. Let me read part B again, guys, just to make sure if I didn't mess up. Okay, yeah, that's fine. I'm fine. Okay, so be careful, guys. Now they're saying two married parents. So these are the two groups that have two married parents. There are two groups here, and they're clearly disjoint. All right. The first group has two married parents, and they're both in their first marriage. In the second group, you have two married parents, but at least one has been remarried. So if you read part C carefully, you know we're talking about these two groups and they are disjoint, and you have to understand the concept. You have to understand the problem. They are disjoint. Okay. If you have two parents and they're both in their first marriage, you belong to one group. And if Amy has two parents and at least one of the parents, one or both, that's at least one, is has been remarried, she belongs to a different group. These two groups have nothing in common. They won't overlap. So I'm going to say, I'm just simply going to add. I'm simply going to add to get C. Add the two disjoint probabilities. Remember I told you we're gonna do some problems. Now we will use those ideas. C is this, and that turns out to be 45, 61, if I'm not mistaken. So about 60% of the kids have both parents at home. Right, let's see what else is going on. What is the probability that a randomly selected family with at least one child younger than 18 of age has at least one parent at home? Mhm. Careful. At least one parent. What does that mean? At least one means either one or both. Okay? So this time around, you're going to include the single parents and cohabiting. I'm going to include all four. All right? Now, again, let's go over it. Two married parents, at least, do they have at least one parent? Yes. Two married parents, one or both remarried. Yeah, they have at least one parent. Single parent. Yeah, they have at least one parent. Cohabiting parents. They have both. Cohabiting, the term means there are two people involved. So I'm going to involve all those. The only one that I will not include, is no parent at home. Now, since I know this is a probability model, they're mutually exclusive, I can simply add 0.46, 0.15, 0.26, and 0.09 Or I can use that nice trick. I'll tell you what I mean in a minute. So the event of having at least one parent and the event of having no parent at home are complementary. So if I know this probability, 0.05, I can just subtract it from 1 and I'm going to get 0.95. Now, uh, that's one way of doing it. Another way, you can simply add 0.46, 0.15, 0.26, 0.08. Trust me, do it. You're going to get the same 0.95. All right. So, guys, I have assigned some problems. I'm going to stop the lecture now. This is our lecture. I did assign problems from 5.2. Try them. If you have trouble with some of them, um, please ask. We will work on them on our next recording. All right. Have a good day and feel free to contact me if you need help and do the work, learn something from the course. I know it's it's not a it's I don't think it's a course that's too difficult, but this is my opinion. But again, I'll be happy to help you and keep in touch. If you can do some of the problems from 5.2, please give me a clear screenshot. Don't tell me number five. The number five you saw it may not be the number five that I will see. All right. So give me a screenshot. I'll be happy to do it next class if you have any questions. Bye bye.